Okay, so we're recording right now, and let me go to the slide presentation from the current slide. Yes. Okay, so I'll share the screen. Okay. So today we'll start. We'll move to mathematical induction. And let me connect my camera, because at some point I will be using like a whiteboard thing. Okay, it's showing the whiteboard now. Can I not do that? Hold on. Hold on. So if you know what, I guess it will just keep on showing this instead of my face, but maybe that's okay. So what do you see right now? Do you see slides, or do you see me? Or do you see my whiteboard? You see both. Okay, but which one is bigger, the slide? Or slides are on the main screen? Thank you so much. Okay. Well, so I guess you will be deprived of the pleasure of doubtful pleasure of seeing my face, and we'll just go like this. It would be preferable if the empty page is replaced by me, but it's okay. Okay, maybe next time. All right, so it roughly sections 8.4 and 8.5. Okay, and I think I just destroyed the slide somehow, or hopefully not. So induction is a technique for proving theorems parameterized by integers. Okay, and to my dismay, I see that like some edits I put on the slides didn't make it to this version. I'm not sure how, but anyway, I'll put the edited ones on the online. So here is an example of what we mean by theorem parameterized by integers. Here is a theorem that says that for every integer at least one, the following statement is true. And notice that this is a statement about this integer n. Definitely, the statement says that two things are equal. The right-hand side is some numerical expressions that can be evaluated given n, right? It's n times n plus 1 over 2. And the left-hand side of this equation is also a numerical expression that can be evaluated given n, because it's a summation of a sequence of j's going from 1 to n. So it's basically 1 plus 2 plus 3 plus 4 plus plus n. It's a summation over a sequence of n elements. And so given n, this has some numerical value that depends only on n, right? Because this is this summation, its value depends on n. So whether or not this equality holds is a predicate about n. So that's what we mean by a statement parameterized by an integer. It's a statement that for some range of integers, here n greater, all n greater or equal to 1, some predicate about the integer holds. This predicate is here expressed as equality of between these two numerical expressions, both of which depend on n. And given n, you can evaluate whether this predicate is true or not, right? Well, and the theorem says that actually it will be true for all n's in that range. So here is the predicate explicitly. The predicate P of n involved in this theorem says that the sum of the first n positive integers equals this numerical expression. So this is is an example of a statement parameterized by an integer that we will use induction to prove. So think of this, have this example in mind, and just in a more abstract way, take any predicate about an integer, like for example, this one that you just saw on the last slide. And the if theorem is of the form that for every integer greater or equal to some threshold value, here 1 for the simplicity of an example, that some predicate about this integer is true, and just think of this predicate as an example, then you can prove such theorem by doing two things. First, doing the so-called base case. The base case is the proof that, okay, this theorem says that for all n greater or equal than some initial smallest value, the predicate is true. The base case consists of proving that this statement is true on the smallest value, 1 in this case. Okay? These are, by the way, arbitrary. Like, we will see examples where, like, if we start at some other integer, not 1. The second part of the proof is so-called inductive step. And that's a proof that a certain implication holds. The implication must hold for all integers greater than the threshold value, that if the predicate holds at point k, then it also holds for point k plus 1. In other words, if the parameterized statement is true about some integer, then it necessarily must be true about an integer 1 more, that one. And these two will combine to prove that this predicate must be true about all integers, starting from this smallest one. You can what you're proving in the inductive step is an implication. It's an implication that says, if my parameter fits is anywhere greater than this point, and the predicate holds for that parameter, then it must hold for parameter 1 more. Why these two? So the P1 is true, and that this implication is true. Why do they imply that Pn is true for all integers greater or equal to 1? Well, so let's do it sort of by hand. Definitely that P1 is true, that just follows from the base case, right? That's the base case explicitly. Now, what about, I want to know whether P2 is true. But if I instantiate the inductive step with integer k1, then what inductive step says when instantiated with k equal 1 is that P1 implies P2, right? Because 1 satisfies this, this part, and the inductive step proved this for all k. Therefore, in particular, it proved it for k equal 1. And for k equal 1, this says P1 implies P2, which is this. But now we know that P1 is true by base case. So the combination of the fact that P1 is true and that this implication is true implies that P2 must be true, right? Because otherwise, a truth cannot imply false, or otherwise this implication would break, right? Would be contradicted. So the consequence must hold as well. So you know that P2 is true, and now use this inductive step, instantiate with k equal 2. Again, this part is satisfied, and for k equal 2, what does this inductive step say? It says that P2 implies P3. And since you knew that P2 is true, again, if this implication must therefore imply that P3 is true, and so on and so forth, right? So basically, you run the base case to establish the ground truth that the predicate is true about the first integer wherever your range starts. And then as many steps, inductive steps as you need, you instantiate first for the first integer, p1 will imply p2. Now take k equal 2. p2 will imply p3, and so forth. So to establish that Pn holds for any n, which is what I want, right? That it's true for any n. Okay, so take that n. It is some finite value. I will show you that this is true because invoking the base case gives me that P1 is true. And then invoking the inductive step n, or actually n minus 1 times with k ranging from 1 to 2 to 3 to 4, etc., eventually will imply that all these guys, P1, P2, P3, blah, 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 they're all true. And the n minus first application will tell me that Pn is true, right? It's like dominoes. The inductive rule says that if the earlier domino falls, then so does the next one. That's basically what this inductive rule says, right? Kth domino falling implies k plus first falling. So therefore, if the base case says make the first domino, the first domino falls. Okay, sorry, false sounds like F-A-L-S-E, so drops. Okay, the first domino drops, and the rule says that if k drops, then so must k plus first. All dominoes will drop, right? It's the way induction works is very similar to the way programming works. You have the beginning of your loop is initialized, and then the rest is just some loop that is making something about next integer in terms of the previous one. What this loop, quote unquote, does is that it establishes truthfulness of the predicate at k plus 1 based on the truthfulness of the predicate at k. Okay, so let's go to an example of we have a theorem that we started with, right? There's a sequence of summation of the sequence of the arithmetic series starting with 1, ending at n. The closed formula for that summation is this, n squared plus n over 2. So let's recall what's an inductive proof in general. If I'm proving some arithmetic, some statement that is parameterized by an integer, and I'm proving it for all integers, I want to prove it for all integers greater or equal to 1, then I have to prove that this predicate on n is satisfied for the first integer in my race, that's in my range, that's base case. And then in the inductive step, prove that for all integers fitting this range, predicate at k implies predicate at k plus 1. So, and here the predicate says, again, that the summation from 1 to n is this closed formula. It is convenient to express such a predicate as, and it's not always the case. So some predicates are of this form and others are not. You know, a predicate could be that some Boolean formula is true and, you know, it doesn't have left-hand side or right-hand side. But if you have a numerical equation where left and right-hand side are both somewhat complex, then it's useful to think of this as some function of n, and I will call it a left-hand side function. And this is some other function of n, I will call it right-hand side function. And the predicate says that the left-hand side function and right-hand side function equal. So what's the base case? Well, the base case is this predicate instantiated with n equal 1. So in other words, that this formula summation up to 1 is the same as this closed formula inserted with n equal 1. Well, summation is easy. From 1 to 1, if I sum, I just get a 1. Yes, because it's a summation of arithmetic series starting at 1 and ending at 1. Right-hand side, if I put 1 here, I get 1 plus 1 times 2 over 2, that's 1. So case closed, right? Left-hand side is indeed equal to right-hand side, and the predicate holds. So this equality holds for n equal 1. Now, what about the inductive step? So in the inductive step, we have to prove that for all case, this predicate instantiated with k, this equality when for n equal k, implies that this same equality, but instantiated now with k plus 1, holds. So which of these matches this pattern? So my ranges are correct. So in each of them, I want to prove this some implication for, okay, well, so it's not this one, because what I want to prove is an implication, right, of this form. For all k greater or equal to 1, yes, all BCD match. And the implication I need to prove is that this formula inserted with k implies this type of equality inserted with k plus 1. Which of these is that? Oh, I see chat is dead. Okay, but some people do say C. Okay, good. Yes, it is, right? Okay, what has happened now? I'm not really sure. I pressed the button and everything I had just disappeared. Okay, hopefully you still see my slides as I do. So yes, it's this one, right? Because this is this formula instantiated with k, and this is the same predicate instantiated with n equal k plus 1. That's why it's sort of mentally easier for you if you don't use n in these implications, because it's easy to be confused. N plus 1, where I have n plus 1 here, so what's going on? No, do this, change the variable, make this implication for some other variable like k, instantiate this formula for k, boom, and now instantiate the same formula for k plus 1, boom. This is what you're proving. This is what you need to prove in the inductive step. Okay, so now is the time that I want to switch to so let me just try to do this so that spotlight for everyone, maybe, no, removed all pin videos, no. Hold on. I guess I just have to stop sharing and then this thing will come up. Hold on. View. Speakers
it works.
view. Yeah, so it worked. Okay. It's unfortunate that you guys lost. Okay. So we will just try to toggle this way. So this is what we're proving. For all k greater or equal to 1, if summation, is this readable? No, it's not. Not really. Okay, better. matter, hold on. Okay, that's better. For all k greater or equal to 1, if the summation j from 1 to k over j, right, the arithmetic formula equals k plus 1 over 2, then the arithmetic summation and which ends at one step next will be the same formula, but instantiated at the next step. So this is what we were proving. This is what we are supposed to prove, this implication. And this thing here is my predicate instantiated with k, and this thing here is the predicate I wanted instantiated with k plus 1. Okay, so it has the form that you expect. Okay, and so my technique, okay, for going for proving these things would be: this is the goal, this is the assumption. What in the goal can be related back to the assumption? How can this assumption be useful in proving this? And perhaps it's not immediately apparent. So I'll claim that it's useful because this left-hand side has a very clear relation to the left-hand side here, because summations are really recursively defined, they are really recurrence relations. So a summation of some arithmetic series ended at k plus 1 is a summation of the same series ended at k plus one more element in the series. So there is a clear relation between these two. And how does this relation go? Okay, so summation over j's from j equal 1 to j equal k plus 1 can be rewritten as a summation from j to k of this arithmetic series plus one last element whom I'm not counting here. And what is that element? It's j for j equal the last, which is k plus 1. Right? So simply speaking, sum over integers from 1 to k plus 1 is the sum of integers from 1 to k plus the k plus first integer, right? So this is by summation definition, right? So if we know what summation is, then this follows. And now we are in great shape because this thing here is explicitly this guy. So therefore, we can use the assumption that the predicate held at k to rewrite this left-hand side by the right-hand side, which we'll do right now. So we can rewrite this term as this one, and we cannot forget this one, right? So this rewrite is by inductive hypotheses. Excuse me, by inductive hypotheses, i.e. By the fact that pk held. Okay. So that's great because by already, basically, this is an arithmetic formula. Well, it's not yet this one, but basically, there's no longer induction, there's no longer summation. It's all about arithmetics. Is this arithmetic formula equal to this arithmetic formula, right? I don't need to know any of these higher abstract concepts to argue this. Okay, so, well, the rest is like how rusty your arithmetics is, right? There's k plus 1 here and there's k plus 1 here, so I should put them, this is some product of k plus 1 and this is some product of k plus 1. So I will do that like this. right? Because, so I just take 2, multiply this by 2, and right, I just bring them to the common denominator. That's what it is. So this is just arithmetics. And this is k plus 1 is the common term, right? And what is k plus 2? So this is k plus 2. And this now shows that therefore pk plus 1 holds. I didn't really prove that pk plus 1 holds. I proved the implication that pk implies pk plus 1, because at some crucial point in the argument, I needed to assume that pk holds. So this shows that pk implies pk plus 1. And I didn't explicitly use the fact that k is greater than 1, but I did. Otherwise, this summation would be undefined. Okay, so that's the inductive proof. Actually, if you want to ask any question about this page, do so now. Okay. So I take it as a good coin. Okay, how about something else? So now we have inequality by induction that n square is, do you see my slide now? Yeah, yes, I think so, right? No, okay, I take it yes. So what is happening here? The predicate is that do I have the predicate here? No. The predicate is this, that n factorial is greater than n square. And this predicate is claimed for all n greater or equal to 4. Okay, so you see the first example where like we're not always arguing that something is true for all integers greater than 1 or equal to 1. So because this is our starting point, so induction will now, the base case will start from this starting point C, which is 4. Okay, so this here, I have a generalization of the induction slide from before. I don't necessarily start with 1. I start at some constant. I call it C. And what I'm proving is that some predicate is true for all on n, is true for all n greater or equal to that constant. So I have to prove the predicate first on that constant, C, and then for all k greater than it, I will show this implication. Constant is 4 in our case. So why is P of 4, why the predicate holds at n equal 4? Okay, because 4 factorial, 1 times 2 times 3 times 4, that's 6 times 4, so 24. And 4 squared is 16. So factorial indeed overtakes a square at n equal 4. It does not overtake at n equal 3. So 3 factorial is 6, and 3 factorial is 3 squared is 9. And it's also, so for 1 and 2 and 3, this formula is wrong. For 4, it is true. And we claim that it's true for all integers higher. Well, so this is the inductive step. So the inductive step has to instantiate this predicate. It has to show the following implication, that if the formula is true, if the predicate is true about k, then it's true about k plus 1. So the predicate is that a factorial is greater than a square. So the implication, what we want to show is that for all k greater or equal to the threshold value, to the threshold constant, if a factorial of k is greater than a square of k, then a factorial of k plus 1 is greater than a square of k plus 1. Okay, and I can and will use the fact that my k is greater than something in some of these steps. Okay, so now the condition, the border condition will come in explicitly. But the general methodology is the same as before. This is the predicates of the form that the left-hand side is greater than right-hand side. And which of these two we can relate? Well, of course, I can relate this arithmetic formula to this one, right? K plus 1 square is k square plus 2k plus 1. It won't be a useful rewrite. The useful place to start is to look at this formula, recognize that this is a recurrence relation. It's a recurrence relation that is defined. The next guy is the nth guy is n times the value of this at k as n minus 1. So therefore, I envelop factorial explicitly as this long thing, and I rewrite it. Oh, Jesus, what is happening? Okay, I used the wrong animation, I guess. Okay, so this is the point I want to make, right? A factorial at k plus 1 can be written as a factorial at k times k plus 1, right? And that's because of the recurrence relation that defines the factorial. And now I'm in luck because I have a case factorial explicitly here. So I can plug in my inductive assumption, my hypothesis, right? And I can do that because I have to show this for every k greater than 4, and I could assume this for so, right? Okay, I don't know what's going on with the animations, but anyway, at this step, I said k factorial is greater than k square. And that follows by the inductive hypothesis, so by this. And the rest is arithmetics, right? Because now I have an arithmetic closed formula, some cubic polynomial. And all I have to do is to argue that this cubic thing is greater than this quadratic thing. Now, if you think like a second, like, the cubic, with positive constants will always be greater than quadratic, except maybe at some initial cases. That's why we have this part. Because indeed, with these initial cases, it won't work. But here it does. So, okay, so the rest is like, okay, how fast can you argue that this cubic thing is greater than this quadratic thing? It's not obvious how to argue these things. But here is one way. It's not set in stone. You can have a different way. You can have millions of ways to that this expression is greater than this one. But here is one example, okay? I rewrite k squared as k times k, okay, nothing strange. Then the fact that k is greater or equal to 4, I will use to argue that this thing is upper bounded, this cubic is upper bounded by this quadratic. I just take k, the fact that k is greater or equal to 2. I do that because that's all I need. That's all I need to show that this thing is greater than this thing. Because even if I upper lower bound k by 2, then this already is still greater than that. But at least we are comparing apples to apples because this is a quadratic and this is the quadratic expression, right? So now I evaluate, I guess, or perhaps I don't yet. I just noticed, okay, how can I argue this fast? If 2k is greater than k plus 1, then this whole thing will simplify to k plus 1 square. And that's what I do. Okay, I don't know what happened. Oh my goodness. Now I just destroyed this slide somehow. I do not know why that happens, But you know what? I will, oh, and now it's not shared, right? Hold on. Share this. Share. Okay, we're back. Okay, because I messed up animation on the square, so um, okay. Very okay. Um, I think this animation worked on my other laptop or something. All right. Um, so this step, it was used to upper bound k squared by 2k. And here I just rewrote 2k as k plus k. And because all I need is to upper bound this by k plus 1 times k plus 1, which is this. So all I need is that the k is greater or equal to 1. These are a little bit, these steps are like so simple that you might be asking like, what is happening here? Because it seems like kind of obvious, no? But what is happening is that I'm trying to argue that this cubic is greater than this quadratic expression, and that involves some quote unquote obvious steps, but it's not so apparent, okay? So, and essentially any argument that shows that k squared is greater than k plus 1 or equal will suffice and will work just as fine, okay? People have often asked, and in the cases that you will see, you will bump into these. Like, yes, I have some expressions that seems like obviously greater than some other, but yet the obvious part is like, I don't really know how to argue. Well, here is slow broken down into small substeps, so you can have an example of how to argue such things. Okay, here's another example. Um, I have a theorem that says that for every integer n, an expression 5 exponentiated to the power 2n minus 1 is an integer that is always divisible by 12. You can evaluate this and see. But how would you prove this? There is nowhere it's sort of apparent in here that there is some sort of multiple of 12 anywhere here. Okay, and yes, this is indeed the same as 25 to the n. So um, these statements are all equivalent. That 12 divides some integer evenly, it's the same as to say that this integer is a multiple of 12, and it's the same as to say that there's some other integer, j, such that m can be expressed as 12j. We will take this formulation of what it means to evenly divide in the next step, okay? So in the base step, we have to show that 5 to the 2 minus 1 is divisible by 12. Well, that's easy, because 5 to the 2 is 25, minus 1 is 24, which is divisible by 12. So what about the inductive step? We have to argue that if an integer like this is equal to 12 some other integer, then integer like this with one more, minus 1, is also multiple of 12. So in other words, for all k greater or equal to 1, that if 5 to the 2k minus 1 is divisible by 12, then 5 to the 2k plus 1 minus 1 is divisible by 12 as well. Which part expresses this hypothesis? D, yes. No, sorry. But I say in a hypothesis, sorry. This is this one. Okay, sorry, hypothesis. So this first one, and it's this one, okay, because uh, this says that 5 to the 2k is minus 1 is 12j for some j, but that's the same as to say that 5 to the k is 12j plus 1, right? I just carry minus 1 to the other side. Okay, so this is the same as to say that 5 to the 2k minus 1 is a multiple of 12, okay, which is what this says. So, so in other words, if I express the consequent in the implication, right, the claim in the implication, in the same way, then what I will be proving is that if the power of 5 with the exponent 2k is expressible as 12j plus 1 for some j, then 5 to the power 2k plus 1 is also expressible in this way, but for some other integer, right, j prime. And I'm not claiming any relation between these integers. What I'm claiming is that this thing minus 1 is a multiple of 12, and this thing minus 1 is also some multiple of 12. So how do I argue this? Okay, so now again I will stop here, and so I have the page. So again, what was I proving? That for all k greater than 1, if 5 to 2k equals 12j plus 1 for some j, then 5 to the 2k plus 1 else equals 12j prime plus 1 for some j prime. Okay, let's see. All right. You know what? Maybe I will. Maybe that's easier to see. Okay. What can be related to what? This part to that part. Okay. It's this pattern of the left-hand side related of the inductive claim related to the left-hand side of inductive hypothesis that will very commonly be the case. It's not set in stone. You know, I can rewrite these things opposite, and of course, therefore, the right-hand sides would relate, right? And for some stuff that I will claim, there is no left-hand side. It's not about equality of any two expressions. But anyway, this will often work. So how do I relate these two? Well, let's see. So let's try to see what that is, right? So this is 5 to the 2k plus 2, right? I just multiplied in the exponent. Well, so that's the same as 5 to k times 5 to 2, which is the same as 5 to the 2k times 25. Okay, now at this point, I will use the inductive hypothesis. So these are just arithmetic rewrites, right? So this is also for, so far, this is just arithmetics. The inductive hypothesis told me that 5 to the 2k is 12j plus 1 for some j. All right, so let me do that substitution and times 25, right? So there exists j, right? So there is some j that makes this expression true. And what I want of this is to express it in this form for some j prime. And because it's a, okay, so let's try to do that. Let's just try to, how can I do that? Okay, let's try to multiply everything. So 12 times 25 times j plus 25. So this is 12 times 25j plus, Well, what would be the useful thing to do with that? Express it as something of this form. So it's 12 times 2 plus 1. And now we are home, right? Because this is 12 times 25j plus 2 plus 1. So all of this is just arithmetics. The point is I needed what I wanted. This is my j prime. So therefore, j prime exists. That's all I wanted. I don't really care what integer, and it is an integer, right? So that's another thing I needed. But of course, if j is an integer, then 25j plus 2 is also an integer. So this is an integer. So I'm done. Therefore, p of k implies p of k plus 1, right? This was p of k, and this was p of k plus 1. Note that sort of for the first time, p of k, the predicate, is a quantified formula. The predicate here, p of n, was that there exists an integer j, such that 5 to 2n minus 1 equals 12 that integer. So that this whole thing is Pn. And it involves it's a quantified formula. Okay, that there exists some j which makes this equation true. And okay, but all that, that complicated the thing maybe somewhat, right? Because I didn't drive to any particular expression here, but I drove to an expression that was 12 times something plus 1. And all I needed to rewrite these things with is so that I could get there, so that this, whatever this thing was, it can be expressed in that way. If you know what's your target, then you will see how to get from here to here. Okay. Okay. I have another proof on the slide, but obviously I will start next lecture with that one. And I will take questions. Maybe if you don't mind, I mean, you can protest on the chat if you do mind, but let's record questions because they may be useful for viewers offline. But if you don't want to record, then I can just stop recording too. So it's now open mic. Is there some of the stuff you want me to go over?
Professor, I believe there's a question in the chat.
All right, and what is it?
Someone is confused where the 25j plus 2 came from.
25j plus 2, hold on. Here?
Your final step.
Wait. The first occurrence of 25j is here. And that was because I multiplied 25 by 12j. So that was 12j times 25. So that's where 25j came in. Here I just grouped it. And here is just a repeat. Let's call these first 2, 3, 4. Okay. Ask me which line troubles you. Oh yeah, this 25j plus 2. Oh yes, this is 25j here and 2 here. All right, so I take these two and combine them. All right.
I have a question for the last statement. For the
Mm-hmm.
exponential one. What do you mean to say by that? I don't. Maybe I missed it, but I don't actually know what you're trying to say. Not the one after that.
This one?
Hmm.
This one, I'm just repeating. I should have said this at the very beginning, that this is the predicate that we are proving. I mean, it was on the slide before, but it's better to bring it up here. This is a reminder that the predicate we are proving. So in this whole thing, we're proving that for all n greater than 1, Pn. Okay, so this is the theorem where Pn is a particular predicate. The predicate is this one. The predicate is that 5 to 2n minus 1 is divisible by 12. And the way to express that is using a existential quantifier, that there exists some integer, j, such that 5 to 2n minus 1 is 12 times that integer. So this is the rewrite of the predicate that said that 5 to n minus 1 is divisible by 12. So that form was given on a slide, or I believe actually it was that 5 to n minus 1 is a multiple of 12. Okay, all of these are equivalent. And this one is also equivalent, right? Because it just says that there is some integer that 12 times that one makes this one. And the reason I want to use that one is because it allows me arithmetic movements, right? It's like once I realize that this is what the predicate says, I can take this j and I can use it. I just used it in here, right? And now it created this j prime that I needed to instantiate the same predicate at k plus 1. So all of these predicates are this, it's the same. It's one and the same predicate expressed in 3 different ways. This way is most useful for arithmetic manipulations.
Professor,
Yes.
could we go back to the previous proof that you did on the inequality? The one where it was n factorial is greater than n squared. If you could go to
Sure.
the last,
Hold on
where
a
you're
second.
doing the work.
So yes. Hold on. Where am I? Okay. This one.
Yeah, could you explain from 5 if you don't mind?
Yes. So the fifth, this movement from 4 to 5 is okay, right?
Yeah.
Okay.
I can.
Okay. And now, from 5 to 6, all I do is that 2k. So this is 2k. I just replace it by k plus k, right? Which is equal to 2k. K plus k is equal to 2k.
Yeah, got it.
That's right. And then I just upper bound k by 1, which I can because it's actually upper bound, it's not upper bound, it's lower bounded. K is greater or equal to 1 because it's actually greater or equal to 4. So this also is true. 6 to 7 step is a true step, right?
Okay.
Just because k is greater or equal to 1. And the reason I wanted to get here is because this thing is equal to this thing.
Okay, and the reason you were able to upper bound it by 1 and also, sorry, lower bound it by 1,
Yeah.
and in line number 5, you lower bounded it by 2 is because k has to be equal or greater than 4.
Yes, yes. So that those parts would actually work even if k was greater or equal to just 2, but the base case would not. So the base case only worked for k equal to 4, right? The implication, actually, what I used here is that k is greater or equal to 2. It's also true whenever k is greater or equal to 4, but what I used is only that this is greater or equal to 2. And the bottom line is that, whatever series of rewrites that will let you argue that k squared is greater than k plus 1 is fine. But that's what was happening here.
Okay, and you chose 2 just so you could get to k plus 1 times k plus 1, right? Just so you could like break it down to that step, correct?
Right.
Okay, got it.
Right.
Thank you very much.
You're welcome. Also, you can think that, this equation, it will work. It does not work for k equal 1, right? Because you have 1, and here you have 2. But it works for every k after that. So for case 2, this is 4. 2 squared is 4. This is 3. So that works. The bigger k is, this is gonna grow much faster, right? Because it's a quadratic, and this is linear. So this will always be greater than that afterwards. And so it is true. And but now you do have to do some gymnastics to make sure that everybody knows it's true. By the way, if on the test you have your series of rewrites will rely on some arithmetic property, and you run out of time, you're trying to how do I argue this stupid property? Like, it's obviously it's true, but I don't know how to argue it. Just say it. The rest of the proof relies on this fact. I claim this is true for all k greater than 2. I ran out of time to show it. You will most likely get like almost all points for this, right? Because this is arithmetics. Like, we don't really care so much. I mean, we would love you to be able to argue stuff like this, right? Like, and just to refresh your, whatever, elementary school math. But okay, perhaps you run out of time and this is not the key part of this class. And you have an example of how to do it, and you'll have more in practicing this stuff with the lecture exercises, homework exercises, discussions, etc. But it's not a key issue. Like, if you somehow run out of ideas to prove such inequalities, you can just claim they are true, I guess, right? Like, if you're just completely at a loss. So this is what I'm saying, so that you don't get flummoxed by this stuff. Okay. So I think we will end here. So thank you, and see you Wednesday, and go to discussions and post stuff on Piazza. See you next time. Thank you so much.